Hello, everyone. My name is Jae-Seok Yang, Principal Geotechnical Engineer from Midas IT headquarters. Today's session is on the soil structure interaction for file depth foundation. For soil structure interaction, we need two groups of engineers, structural engineers, guys, and geotechnical engineers. And we are going to cover different soil structure interaction methods, what are different approaches available, and the different efficiency levels, benefits, and so on. That's an overview for the today's session. First, I will briefly walk through the soil structure interaction for building. Then I will overview the substructure indirect method, that is the determination of soil springs for structural design. And then I will present about the direct interaction method by using file modeling in Midas GTS-NX and the case study of file lab foundation on high-rise building. In structures founded on non-rigid formations, the soil flexibility influence structural response and vice versa. This phenomenon is called soil structure interaction, simply SSI. SSI is one of the several factors influencing response to seismic laws that include source effect, travel path effect, and site response effect. SSI is an important factor in many applications, such as terrain include vibrations, vibration reduction measures for soil waves, and machine foundation vibrations, and seismically loaded structures, and so on. The substructure method is based on the principle of superposition, separating the first two causes of the interaction, the inability of the foundation to allow the free field displacement, and the effect of the dynamic response of the structure foundation systems on the movement of the supporting soils. So in this slide on the left side, this is the substructure method. Is basically by using the simple spring theory for the soil, which is generally used by in the common structure software. So this method is limited to analysis of nonlinear systems or linear equivalent because it is based on the overlays. But when it comes to the direct method in the right-hand side, the soil structure system is modeled and analyzed in a single step. The excitation movement of the free field is carried at the base and at the boundaries of the model. And the result of the response of the interaction system is called calculate from the equations of motion. This method requires the computational software program that can treat soil and structure behavior with the same rigor. So it is used by the software ژئوتکنیک one by using both the finite element or finite difference method. As schematically depicted in the figure, the soil is often represented as a continuum. For example, finite element along with foundation and the structural element, transmitting boundaries at the limits of the soil mesh and the interface elements at the edges of the foundation. Direct analysis can address all of the SSI effects described above, but incorporation of kinematic interaction is challenging because it requires the specification of spatial vibration, input motions in 3 dimensions. Because direct solution of the SSI problem is difficult from a computational standpoint, especially when the system is geometrically complex or contains significant nonlinearities in the soils or structural materials, it is rarely used in practice. Next, I will overview the determination of soil springs for structural designs. So structural engineers use spring to present the soil as we see in this slide. For a given column load, for the foundation effects representing the soil settlements and the spring represent the soil pressure, On the other hand, geotechnical engineers model the soil as a continuum, either as an elastic space or an inelastic space to determine the corresponding soil settlement and stress due to the column load. So this is the simple equations. Maybe you are familiar with the determination of what the soil springs are, especially under the left. The K value is the subgrade reaction values as we refer to it, which is also known as the Winkler spring, or modulus of subgrade reaction is the ratio of the soil pressure over displacement. So the unit is pressure over strength over the length. Now the foundation response, the significant difference between Winkler and continuum model is as below. This can be demonstrated easily by examining two extreme situations, a rigid foundation and a flexible one. And you will see the contact pressure and settlement between these extreme situations. For the case of the rigid left, on the left-hand side, we have the structural approach of Winkler spring model, and it's a single set of Winkler springs, which is on uniform settlements and the uniform stress distribution. However, in ژئوتکنیک approach, as you can see, the settlements may be constant, but the stress distribution is not. The high stress developing at the edge of the left. Now, by definitions of the springs at the edge of the left have to be higher than the springs at the center of the left to capture this stress behavior, while you have higher stress but the same settlement. Now, in the case of the flexible left, in the left-hand side, you have the case of the single set of springs, which gives you uniform settlement and the uniform stress distribution. However, elastic theory shows that the stress distribution under the left is going to be constant, as the post that we had at the previous case, but the settlements are going to vary. The highest settlements are carrying at the center of the left, and the smallest settlement carrying at the edge. Again, based on the definition of the Winkler springs, you will expect higher springs at the edge and the lowest at the center. So what is the solution for this? The solution is that we should not use the one zone of springs, but at least two zones with the outermost springs being higher than the springs at the center. Now for steep soil, outer springs may increase about 30 to 40% compared to the springs at the center, whereas the soft soil, we will have to increase 2 or 3 times compared to the springs in the center. Again, the steep soil and the soft soil is relative to the foundation steepness and the loading, and even rock would need to use 2 zones of springs. So this slide shows that different method to determine the K value, also known as modulus of subgrade reaction. Method A consists of the plate load test. You calculate the values from the test stated in your textbook. They are not appropriate for the left design because they only apply to the areas at 1 foot by 1 foot scale. Method B consists of taking the same values, and it is a crowd method. So the most appropriate method is method C, where you will model the locate foundation probably with the finite element method. So now for method C, how you could do that is ژئوتکنیک engineer will estimate the settlement and the bearing pressure at many points within the left, and they will determine many K value based on the pressure of settlement design, and they will draw the contours of the K value and determine accordingly what kind of zones to assign and what kind of K value assigned to those zones. Now I will present about the calibration and the direct interaction method by using file modeling in Midas GTS NX. So as you can see in this slide, you will see this example of the file left foundations. So there are various kinds of interaction between, such as the, for example, fire and soil interaction, and between file interaction, and between left and the file, and between the left and soil as well. So in order to consider this various kind of interaction, we have to consider the interface, a kind of interface element in the finite element software in the geotechnical engineering. So the model should be able to consider in the software finite element, for example, three-dimensional behavior of a file left foundation. So we need to think it 3D for that. The applied constitutive laws should be able to take into account the nonlinear file, soil behavior at file left shaft, and the file base. The stress strain behavior of the soil depends on the applied stress path and the strain level. And the model should be able to simulate the behavior of a single file to check its reliability and to adjust the applied parameters depending on the chosen file type. So the applied model should be able to consider the different interactions that govern the behavior of the file left. So this is a workflow typically to model file left. Maybe we'll start by creating the numerical model and filling this numerical model by input parameters from geotechnical reports, from lab test and the field test, and also from file load test as well. So you probably will create a single file model to calibrate parameters for this file model, and this will be using for feeding your final of your numerical model of the completed file draft. And you are on your simulation, and you will get result in terms of determination, stress and strain force in the files, and you can also time repro parametric study on so variation of the layout of the file and the diameter and the length as well. And also different load combinations. If you have different combinations, refer to structural load, wind load, earthquake load, and combination of these. And at the end, you always end up with a set of structural parameters that you come up with. And if you do the separate structures design most of the time, you hand this to the structural engineer to use it for structural design of the superstructure. And there are always interaction between structural engineers. So this is a typical flowchart for the numerical analysis for file left foundation to enable structural design. So to quickly determine the iterative process between the structural engineer and geotechnical engineer, the structural engineer provides the column rows to the geotechnical engineer who has already developed an model of the foundation of the soil, and the geotechnical engineer evaluates the foundation settlement and the stress and provide to the structural engineer with Winkler springs or soil springs. Then structural engineer runs their model and they determine the foundation settlements and the stress under the left. And they compare with the geotechnical engineer, and either they are closing up or the geotechnical engineer needs to revise the springs and come up with the new foundation settlements and stress. This process keeps up going until the settlements between the structural model and geotechnical model are converged. So when we use the software, geotechnical one, in case of in this presentation, we are using the GTS-NX from Midas. We can model files with the 3 different approaches. So actually, in general, in 3D model, numerical model, you can simply consider the file itself with the solid element, but sometimes it is more efficient to use only the line type file element. For example, if we have the file left foundation with a number of model files. So this slide shows that the typical solid element for the file, and you can see that the solid for soil and the file, and also you can consider the interface between the file and solid. But please keep in mind that the nodal connectivity is required on file out of surface. And This requires, for example, the number of elements in the model. So therefore, you have to spend much time to calculate the analysis. So this is the reason why we simply use the line element for the file itself. So this is the line to solid interface in GTS-NX. So the concept is the same with the solid for soil and the general beam element for file. And in order to consider the interaction between file and the soil, we have the special interface element, which is the file interface. So this file interface can consider the skin friction as well as the tip bearing capacity as well. I will explain in detail in later slide. So one more beneficial using this special element is you don't need to consider the nodal connectivity between the soil and the file. So, and in case of the number of file with the file left foundation, also it is very well suited for this kind of the huge 3D model. Again, the file and soil geometries and meshes can be specified independently, and the interaction of line and solid elements are calculated automatically. And the mesh requirement requirements for the soil are minimum. So finally, it will be you don't need to spend much time. It can be reduced the computation time during the analysis. And this is about the file tip element. So at the bottom of the file, you can consider the tip bearing capacity as well. So the file tip can be arbitrarily placed in the solid element automatically as well. And this slide shows that some of the comparison between the using the solid element and the file line beam element for file. So it is known that the file element typically was for the actual behavior load compared with the solid element, but in case of the lateral behavior is expected that it is better to use the solid element rather than file beam element. And this is the dialog box of the software. So in this dialog box, as you can see, here is the input parameter of the file interface. So as I mentioned, the first one is the ultimate shear force. And next one is the shear stress modulus, and the normal stress modulus is related to the file interface behavior between file and soil ground. And this one is related to the tip bearing capacity. So first one is the file tip capacity value, and next one is the tip spring difference between file tip and the soil. So again, this slide explains that what I explained, what I comments in the previous slide. So again, the ultimate shear force in this graph, this is the maximum value of the kind. You can obtain this value from, for example, pilot test in the field. So this is the graph with the shaft friction and the relative displacement. And the ratio of the shaft friction and with the displacement is the input of the shear stress modulus. So file bearing capacity is input in file elements and not a result of the calculation in the FEM software. The purpose of using the file left foundation analysis in geotechnical software is to check the deformation behavior due to the superstructure, including the building or bridge. So again, this shows the schematical image of the file element, interface element with the file tip. So So this already I explained, so I will skip this. And of course, when we develop this special file interface element, we also did the validation for this when it introduced in the software GTSNX, and we tried to re-simulate one of the example where there have been extensive monitoring these days, and all the example is filed, and all the highway bridge in German is those presented by the researcher. And it shows the full pile load deformation behavior, such as the total load, skin friction, and the base load. And we have simulated the exact same file behavior. So the file is actually 1.3 meter diameter file and 9.5 meter length in the pilot test. So as you can see in this result graph, so we have to simulate this using embedded file technique element, and we are satisfied with the behavior we could capture, the total load behavior, skip friction, and the base resistance. So we can say that we can capture in the reasonable way as an individual component. So GTSNX can import model information such as the meshing, material structure, cross sections, and load and boundary conditions from Midas family software, Midas Gen. And the CAD interface transfers project data for expanded analysis requiring soil structure interaction and detailed 3D investigation such as bridge pier and highlights building foundations. So in the first case, you can see that on the left-hand side, this is the model from Midas Gen. So as I mentioned that the whole model information can be exported into GTSNX, then you can simply create the ground modeling since the superstructure already you have imported from Midas Gen. So this is the very typical and important case to check the side or kind of the risk assessment of the superstructure building during the tunnel excavation. So maybe you can expect that during the tunnel excavation that some of the settlement can occur above the superstructure buildings. So generally, maybe you know that in the geotechnical software, you can just simply apply the pressure load or point load to simulate the structure building. But in that case, you cannot check some of the deformation behavior for the structure during the excavation. So this is the only way that to check the deformation or behavior of the structure buildings during the tunnel excavation into the software geotechnical, including the real building structure modeling. So this is some of the example that we had the interaction by using the case. On the left-hand side, again, the Gen model, some of the stadium structure and the apartment. And you can import this model into the geotechnical software GTSNX. And some of the structure again. So finally, as I mentioned that you can check some of the behavior of the superstructure after calculation analysis in the geotechnical software, such as the stress and the displacement as well. And after that, so in GTSNX, we provide that to calculate the spring stiffness values, again, by using the stress of the soil divided by the settlement or displacement of the ground. Then this subgrade reaction value can directly revert to the Midas Gen, and then by using a kind of text file, and then the previous spring value can be replaced with the new spring value, which is the calculate from GTSNX. As you know that the spring value calculated from the geotechnical software is more realistic. You know that realistic rather than the simple spring value by using the, for example, Winkler theory. So we use the elastoplastic model such as the Mokulong or hardening soil model, which is developed by simulating the real ground behavior. So the spring value calculated from the geotechnical GTS-NX software is finally used for the design of the structure in Midas Gen. Lastly, let me introduce about the case study by using the Midas Gen and GTS-NX with these interaction features. So the building, which is focused on the presentation, is 55 story, about 168-meter tall, designed in a layered soil of the low resistance. And because of the size of the building and the soil pounded side, soil structure interaction was necessary to evaluate the settlement and the behavior of the structure. The structure team did not work with the Midas Gen, and their platform did not export to Revit or another. So it was impossible to directly import their model. So the geotechnic team replicated the design and the structure of the same geometry, same load, and the same case used by the structure team. So this model was fully created in Autodesk Revit. With the Autodesk Revit Midas Gen link, the structural model was exported to Midas Gen. And after applying some conditions from Gen, the model was finally exported to GTS-NX, where the full model with the ground was analyzed. I said the building comprised 55 story, resulting in 168-meter tall, meaning that one of the top tallest building in this country. So the whole structure is designed in reinforced concrete, and each story has an area of about 440 square meters. We have a total of the 18 columns, which are on actually structural walls because of its size. And the total dead load is about 300,000 kilonewton. Some other building details about the foundation. It is a file wrapped foundation with 106 piles, continuous flight over type piles. So each one with 100 centimeter diameter and 30 meter long. The left has an area of about 680 square meter. And we can check the image in the left, which is on air view. By this phase, the pile was already done, and what they were doing was excavating to them to construct the left. Now we move to the soil characterization. In this site, we have 5 standard penetration tests close to 50 meters deep, and also 4 cone penetration tests which reaches depths close to 43 meters. So this site is located in the southern coast of the country, and its profile comprised a layer of sand and clay due to the characteristic of its sedimentary deposit. With the result of the pH contest, we can see the excess of water pressure starting from the depth of closing to 14 meters. In this slide, I will show you some result of file capacity prediction based on the cone penetration test. So here we are heading to the file load test program. The static file load, just to define, it is composed by a real scale file, which is tested by applying load, and by the same time, the settlements are recorded for each load step, and the figure in the right shows the test scheme, which is basically composed by the test file and the reaction files. The program of file load testing was undertaken, which included 3 continuous flight over files test to the maximum load of close to 9 meganewton. The static load tests were undertaken prior to the foundation construction, which allows you better understanding of the behavior of files. The result of the file load test were compared to the values obtained by the circle approaches using method of SPT and CPT. As can be seen in the load settlement curve, there is difference between them. And the provision of the behavior of file based on the CPT shows much closer for those measured file load tests, which distribute mostly explained because of the nature of the test, which is much more technical than the SPT. And in GTSNX, the result from the file load test were used to define the properties of the file. It is very important to have file load test when designing the building foundations, especially high-rise buildings. So let me show you a little bit more about the file load test program. These are some pictures of the test. The figure shows the file load scheme composed by consider the hydraulic jack, which applies a load and that reacts against the reaction frame. In this case, we had 4 reaction files to resist the force. Also, the important equipment is the load shell, which allows us to read the load more accurately. The geotechnical design starts with the design of the file load test. So we define the type of file, the diameter, the length, the maximum test load, and also the reaction system. We followed up the execution of the test and later interpreting the result. Now, heading to the structural model started in Autodesk Revit. As I said, the structural team did not work with Midas Gen firstly, and in their platform, you are not allowed to export to Revit or some kind of the file that could be imported by Midas Gen. So the geotechnical team replicates the designed structure with the Revit by using some load and the load cases used by structural team, and this model was fully created in Autodesk Revit. All the materials, sections, properties, analytical model, and loads were applied directly in Revit. I will show you a bit of the Revit interface now. So this is Autodesk Revit, and we have the other full model of building here. You can see all the geometry and the arrows which are applied loads. And the thing is that we want to take this model with Autodesk Revit and to export the Midas Gen. So the function which is a link that need to be installed. And if you go to add-ins, external tools, and we have this option. So here, this option, send the model to Midas Gen. So you just choose the name you are going to save it, and here you can choose the element size for slabs and walls that you are exporting. Also, you can choose the unit and just click send, and then it will save the MGT file, which can be imported in Midas Gen. Let's back to the presentation. So this is the view of the model imported to Midas Gen, including all the geometry information, sections, materials, and properties. Then I will show you a bit of the Midas Gen interface. So this is just a new file. We go to the menu and import -gen mgt file, which was exported by Revit. I choose this one that I saved before. And just take a little bit time to open up. Then so as you can see the message, it is imported with no error and no warning. I'll just take a closer view for you to follow up. And you can see the machine showed an option together with the final stage. And also shows in the menu what was imported. So we have material from the concrete that we have defined in Autodesk Revit. And you also have other sections that was all defined in Revit. And we have also this information about thickness of slabs and walls. And we have some boundary conditions, some elastic link, and some beam and release, which were also defined in Revit. And let's see, we have the loads. In this case, we have just applied dead load, live load, and wind load directly on Midas-gen. So let's back to the presentation. So in Midas-gen, some conditions were applied as compounding the story information, initial boundary condition, and wind loads. And then the model was analyzed to check for inconsistencies and comparing the reactions obtained by the structural team on their platform. Those obtained by Midas-gen, the difference was smaller than 5%, which is considered a very good approach allowed with the structural team. The behavior of the model was approved and then exported to Midas GTS-NX to start the foundation process. Let's back to the Midas-gen to show how to export. So we have the full model of the structure here, and we want to export this to open in Midas GTS-NX. And we go to menu, export under MXT file for GTS, and just save it. And later, we can open it in Midas GTS-NX.
Sorry, Mr. Yang, the screen has not been shared.
Okay.
Yes, it's already shown.
Yeah.
Yeah.
So let me show this export again. So we have the full model, the structure here, and we want to export this to open in Midas GTS-NX. We go to the menu, export on the MXT file for GTS and just save it. And later, we can open it in GTS-NX. Then let's back to the presentation. So going on to the geotechnical model inside GTS-NX, soil meshes were created in scale 100 meter by each side with 50 meter of depth. soil layers were created based on the type of soil and resistance. For this case, we have created 7 different layers. Percent, the failure criteria was used the Moklong, in which the result of soil investigation may provide good provisions of values of friction angle. And for clays, the construction model used was the modified camp clay model, which is more complex one with some properties are not defined for very easily. About the file wrapped, we have the 3.5 meter thick wrapped and meshed as a solid element. And the material is concrete, considered fully elastic. Along with the wrapped, we have the, again, over 106 files, which were meshed as line to solid interface. Let me show you the model in GTSNX then. So this is the GTSNX. Let's check it first, the model itself. We have all the soil layers, and let me show you the left of the files. So all the 106 files and the 3.5 meter thick left, you can see now. Okay. So for the file model type, there are some ways to work with files in numerical models. The best way would be to consider a file as solid and find the interface properties and simulate this behavior. But the problem is that the model becomes too heavy to analysis. Solutions that also can be done in GTSNX is to consider the file as a lot of element beam type. So converting a line to beam and creating an interface to simulate its behavior. So the model is equal to the soil, which is composed by solid mesh plus the files, which are lines converted to beams, and the interface line to solid. And let me show you the file. Is actually just lines here. So by using the hidden section, same with the Midas gen, you can show the section with the diameter of the files. And so they have a cross section, and also they have the properties of a file. So we can specify what is their behavior. So trying to obtain the better values, we put them a file load test calibrations. In GTSNX, we have created this simple model to calibrate the load settlement behavior. So the geometry of the file will reproduce different load steps, and the file parameters were changed through trial and error. That is what we call a class C predictions, where parameters are changed looking for convergence with measured values. A load settlement curve shows the file load test resulting along with the fine element model created, and the values of settlement seems to fit well to what was measured. So some numerical model of buildings foundations were made only by applying load or pressure at the base of the columns. It is like retreating the lowest values for each column from the structural team and apply it directly to the model. This might so neglect the distributions of loads in the superstructure and its stiffness or rigidity as you wish. So those results from the real behavior of the structure show higher values of different settlements. Looking to our model, if we try to create a full model, which is the soil plus the file left plus the structure building. And as was said, it is understood that differential settlement behavior seems to be closer than when using other kind of models. Another knowledge is to be able to evaluate different load case directly, and also wind load. And let me show the complete model here. So we have the file left and the buildings, the superstructure, and all the soil layers, 7 soil layers that we have created by this case. Okay. Now, heading to the first result, we have selected here the total settlement. The preliminary analysis tried to satisfy the maximum settlement criteria defined previously for the host structures. And analysis of the different settlements is done, and also calculating the angular distortion, which tends to be more important. As stated before, this model is working with the whole superstructure attached to the foundation. The result of settlement, especially the differential settlement, tends to be more real due to the stiffness and rigidity of the superstructure. Let's take a look at the result. So let's see only the files. In the displacement result, we can check the values of settlement in each file. And you can also select each file's nodes by its top and export these values of the settlement. Here in this slide, we have called the settlement as delta. And then here in the next slide, showing the result of the file loads and the distribution of the load along the file. So it is important to note that file was located in different spots along the left to have different load acting. And this can be evaluated through this analysis using the values of the load obtained to each file and divide by settlement for each file. So we can calculate springs, and those springs are different for each file. The reason of this is mainly because of the positions of the file inside the left, which can be affected by a load location of the column. Due to file group effects, which tends to decrease the deformation of the file, meaning that some may not offer the same reaction as others. So the generated springs for each file may be sent to structure team or simply exported back to Midas Gen, as I mentioned previously. And the very same thing can be done for area springs. This is a file wrapped springs values of the pressure above the left might be divided by the settlement update in the same point. So this is also might be sent to structure team or export to Midas Gen. Okay. So take a look at the result of actual processing files. As the same left, I have said before about extracting those values, and we can extract the value of each file. So these values can be pasted to Microsoft Excel, for example, so we can calculate the spring, and it is easily sent to the structural engineer. Another set of the results are the values of bending moment in the files. So these values are particularly important to define the structural design of files. As these files are continuous flight over files type, the reinforcement case and lengths are very important to be defined, as there is the particularly to insert reinforcement or with length is over 12 or 8 meters. So special procedures might be required as special concrete and also vibrators attached to the cage. So this is the result of the bending moment in files. So we can check the bending moment, and some sides of the left are much higher than from those by the piles in the middle. So finally, some of the conclusion. We consider that we had successful interaction between Rabbit, Midas Gen, and GTSNX. And the key result from Midas GTSNX that we have analyzed are firstly the settlement of the file left foundation, which might be inside the range of the tolerable settlements for this kind of structure. For intersection with the structure team, interaction with the structure team, springs can be created either for each file and also as area springs for left, which are the contact of the file left with the soil. So this kind of information might be repeated, selecting the correct nodes and exporting the values of the loss and settlement. So divide, in this case, area springs, you might export the pressure and settlements and just divide pressure per settlement, then we can get area springs. Normally, interaction between the geotechnical and structural teams are done by several iterations, starting with the setup load sent by the structural team, which result in a set of spring calculated by the geotechnical team. Convergence between both models are being sought, and sometimes several iterations are needed for that. By the time full model is established by using the same platform, the number of iterations needed to converge are reduced. So we really believe that this is a good way to go. As a final comment, we need to measure, and which means that for every effort that we are trying to do involve with complex models, we still need to match the real behavior of this destruction. And in this particular case, every column of this building will be monitored for vertical displacement, since the construction of the very first story, it is to make sure that we are heading in the right way. Another thought is that having some quality soil investigation to retrieve reliable parameters from the soil is crucial, and also have instrumented pilot test is crucial. So the result of our model all depend on the this presentation of this information.